And let's do a share screen. Yeah. Yeah, you can see my screen, right? Can you see my screen?
Yes.
Good.
Yes.
Okay. So let's do a quick recap on what we did last time. That was a week ago. By the way, so first, okay. Hope you had a great time in Yom Ha'atzmaut. One more comment I have about problem set 1. In question number 6, I put things in CGS units. I told you this is normally the way astronomy works in CGS units. Some of you, for an unknown reason, converted it to MKS units and made a mistake, and it's a repeated mistake, so it makes me the good feeling that some of you work together on that, one way or the other. Not that I mind too much working together, provided it's a real working together and not somebody's working and the other one are just copying. But the main point is not that. The main point is don't convert to MKS. Right? Stay in CGS. That's how astrophysics work, and this is a course in astrophysics. It's not that confusing in the end. It's big numbers anyway. Okay, so we're speaking about the principle of equivalence. So we started the experimental, the experiment that lies behind it is the Otvosh's experiment. We chose the equivalent of the gravitational mass and the inertial mass. And this is called the weak equivalence principle. So it has its own name. WEP, weak equivalence principle. And then we said that based on that, Einstein postulated what's known as the strong equivalence principle, or the equivalence principle for short, which states that at every point in the arbitrary gravitational field, it's always possible to choose a locally inertial coordinate system. And within this locally inertial coordinate system, at a sufficiently small region, the laws of physics have the same form as they do in special relativity, so in unaccelerated Cartesian coordinate system. So we don't really need to throw everything we learned about special relativity. On the contrary, we're going to use all of it. So that's basically the way I think of it is this, falling elevator thought experiment, right? Which essentially states that, once you're in a free falling system, such as a closed elevator, there is no way for you to measure gravity. So everything behaves as if there is no gravity at all, right? So the strong equivalence principle. Let's change the color. At every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that within a sufficiently small region, the laws of nature take the same form as in the unaccelerated Cartesian coordinate system. Essentially, we can always find a freely falling in every gravitational field, regardless of what it is, how strong it is, how strange its shape may be. You can always find a freely falling system. And within this freely falling system, everything that we learned about special relativity holds. So that's kind of reassuring. That's the principle. That's called the strong equivalence principle. The short is simply the equivalence principle. That's what it means. And that suggests that the action of gravity is really nothing but curvature of the space-time. Because if in any place, anywhere in space, we can always find a locally inertial coordinate system, then what the gravity really does is just changes this coordinate system. It's just different coordinates in different space, in different regions, right? And that's kind of obvious, right? Because if this is Earth and we are here, right? This is me here, right? My freely falling coordinate system, right, would be falling in the direction of the center of the Earth. And my friend in Australia, which is here, right, for them, the freely falling coordinate system would be, again, pointing, of course, towards the center of the Earth. So it's not the same freely falling coordinate system, right? Of course, we're all feeling the gravitational field of the Earth, right? So the action of gravity is somehow to curve the space-time to tweak these differences between the coordinate, the inertial coordinate system. So that's why we always speak about locally inertial coordinate system. Right? You can always find an inertial coordinate system, but it's always going to be local. My coordinate system and the coordinate system, the freely falling of somebody in Australia, are not going to be the same. There's no global one. From then, got that, then the next thing we did was to demonstrate that this automatically, really automatically, gives the concept of a gravitational redshift. And the idea was to look at two people on a ladder, right? Ayala, which stands up, and Benny, which holds the ladder. But there is a difference of height h between Ayala and Benny, right? And we saw that if Ayala sends a signal to Benny, right, and the way she signals him is simply sending him two photons. So the first photon, photon 1, and then after a while she sends the second photon, photon 2. And then of course Benny receives these two photons. But then the time difference between these two photons as received by Benny are shorter than the time difference as emitted by Ayala. Delta tau Benny is smaller than delta tau Ayala. And that's because Benny stands deeper in a gravitational potential of Earth. And the way we did it was to take Benny and Ayala and says, okay, right, both of them are sitting in the gravitational potential of Earth, but equivalently, we could argue that both of them are sitting inside a spaceship, and this spaceship is accelerated. And because of this acceleration, right, Ayala is sitting right here, and Benny is sitting right here. Because of this acceleration, the velocity of Benny when he receives the second photon is larger than it is when he receives the first photon. And this is equivalence, right? This exactly follows from the equivalence principle, right? Despite the fact that the two photons went through exactly the same trajectory, right? But simply one was emitted after the other. And then we showed that we actually did the calculation, and we showed that result in delta tau Benny is approximately delta tau Ayala times 1 minus GH over C squared, or delta phi over C squared. Right? Now, of course, in reality, what happens is exactly the opposite of this demonstration that I gave. So in that sense, the demonstration is indeed a little bit confusing. What happens is that we are observing in our telescopes signals that were sent to us from Bennu, which is at the surface of the sun, or at the surface of the neutron star, or the surface of any other astronomical object, right? So we can think of ourselves as Ayala, although we are in the gravitational potential of Earth, but as we said, the gravitational potential of Earth is very, very small, because GM over RC squared of Earth is of the order of 10 to the minus 9. So there is a very small difference between what we are observing and what the space telescope would observe. But as I mentioned, this is in your problem set. This is a small difference, but that's enough to, important enough to be considered. Otherwise, the GPS system would not work. But of course, this is much smaller than the gravitational redshift coming from the sun, for example, simply because the mass of the sun is much larger. So that from the sun, it would be something like 10 to the minus 6. From neutron stars would be about 10%. So really, if we are the observers, we are Ayala, and we are watching with our telescopes signals sent us from Bennu at the surface of a neutron star, telling us something about this neutron star, then we are seeing this being reddened, right? Because the frequency that we're observing goes as delta tau minus 1, which means that nu at infinity, right, is nu star times 1 minus gm over rc squared. Right? So the frequency that we're observing is less than the frequency that is emitted. Essentially, photons lose energy as they climb out of the potential well. That's what really happens there. Right? And that's called a redshift. That's a gravitational redshift, not to be confused with the cosmological redshift, which is something else. We will get to that one day, but not today. Right. And then we went on to start to get some mathematical description of the curved spacetime. Now we get to some, let's say, a little bit annoying algebra, but it really is an algebra, right? So again, motivated by what we derived physically, right? Physically, we had two photons that were traveling through the same path in space-time, but there was a time difference between the arrival and emission, which was not the same, and this suggests that the space-time is not flat but curved. So which is essentially what gravity does, right? Gravity just curves space-time. So gravity curves space-time. So we want to know how to, calculate the paths of objects, being photons or being massive particles in this curved space-time. And the way to do it is we just look. So we started by considering a freely falling system. So we start from the elevator, essentially, right? We're in a freely falling system. And the laws of special relativity hold. So the proper time, minus 1 over c squared at the alpha beta, and then I just changed the name of the coordinate, dxi, instead of x and y, x, I call it xi, dxi alpha, dxi beta. And then since this is a locally inertial coordinate system, right? Then free particle, no forces. That means that du alpha over d tau is d squared psi alpha over d tau squared is 0. So in this freely falling particle, we're assuming that we're seeing a particle that is freely falling, no forces. And now we want to ask, okay, but now we're in a gravitational field, so we do see a force, right, which we call it the force of gravity, of course. But I argue that this force of gravity is due to the fact that our system is not inertial, it's continuously accelerating, right? We are sitting equivalently all the time within this flying rocket, right? So how do we calculate the gravitational force when we're sitting inside this flying rocket? Right, we just have to change coordinates to coordinates which are no longer inertial, no longer freely falling, but some arbitrary. So now we look, we expressed the proper time in any arbitrary coordinate system, which I call x mu. Remember, x and psi are two different coordinates, so you cannot mix them, right? It's the same system, but described in different coordinate system. And so we could write down the tau squared, right, minus 1 over c squared at the alpha beta. And now I want to express that in a new coordinate system. So I just write it down as d psi alpha over dx mu, dx mu, d psi beta over dx nu, dx nu, which I just grabbed it together and I call it minus 1 over c squared g mu nu dx mu dx nu, where g mu nu is defined as eta alpha beta d psi alpha over dx mu, d psi beta over dx mu. And g mu nu is also called the metric tensor. But this time in arbitrary field, not in arbitrary space, not necessarily a Minkowski space, in any space. Everything I do is completely general from a mathematical perspective. Right. So now we want to see how the motion of a free particle would look like. Right, this is a free particle motion. So how the motion of a free particle looks like, we just change coordinates. We just wrote down 0, right, is du alpha over d tau, which is d over d tau of u alpha. Again, I want to express it in the new coordinate system. So d psi alpha over dx mu, dx mu over d tau. Right, there is no need for a partial derivative when I do d tau. So I just have to, again, d over d tau, we'll have to write it down as d over dx nu over d tau, d over dx nu. So again, it's just a chain rule, d squared psi alpha over dx mu, dx nu, dx nu over d tau times dx mu over d tau. So that's the first term. And then the second term is just plus the psi alpha over dx mu, sorry, right, d squared x mu over d tau squared. Just a derivative. And then to get things better, I just multiply that by the inverse, right? So I multiply that by dx lambda over d psi alpha, and using the chain rule in the form of d psi alpha over dx mu dx lambda over d psi alpha is just delta lambda mu. And so just multiply it here. And the second term, so like this one, times the second term here, right? It just cancel with the delta. So I end up with 0 equal d squared psi lambda over d tau squared. And then the first term, rather than getting messy with it, I just shorten the notation and write it as gamma lambda mu nu dx mu over d tau dx nu over d tau, where gamma lambda mu nu is defined as d x lambda over d psi alpha times d squared psi alpha over dx mu dx mu. Just some sort of an quite ugly term that appears from this coordinate transformation. But it's quite an important term, so it has its own name. It's called the affine connection. And using the affine connection, right, we can take this equation of motion, right? This is, again, this is the equation of motion of a free particle. There are no forces acting on the particle, right? But S is observed from any arbitrary coordinate system, non-inertial, not an inertial coordinate system, right? And I can simply write it down as just by changing the, just shifting this term to the other side, or maybe I should say this term to the other side, right? And then dx over the tau is just the component of the velocity. So this is just written as d u lambda over the tau, just minus gamma lambda mu nu u mu u nu. And that is the equation. Again, look at what we did here. This is the equation of a free particle. There are no forces acting on this particle. It's freely falling, but it is now observed by an observer who is not in an inertial coordinate frame, but by some arbitrary coordinate frame, which is related to the new coordinate frame, to the old coordinate frame, right? By this metric tensor and the affine connection. And the reason why I wanted to, and of course u is the force velocity in the non-inertial frame, right? So this is u dx over the tau, is the force velocity in the non-inertial frame, right? And the reason why I wanted to do it is because, and this term here, of course, I mean, what is that? du over the tau. This is an acceleration. This is the change of the velocity, right? With the proper time. So if this is the change of the velocity, then this is the acceleration. So this affine connection multiplied by the components of the velocity really gives me the acceleration, as would be seen again by an arbitrary observer, which is not necessarily in an inertial frame. Right? Of course, if this was an inertial frame, right, then, this was just, what am I doing? you know, that means that x would be related to xi, maybe by shift. So when I take the derivative, right, it would just be constant. So it just means that g would be related to eta, and then the second derivative, of course, here, of course, would disappear. So gamma would be 0. So if it was a different inertial frame, I would still see that there is no acceleration. Right? What we did was completely mathematics. Right? Again, it was just algebra, but the important thing is to realize that what is the physical meaning of here. This is how an acceleration would look like in any non-inertial coordinate system. This is pretty much as far as we did last time. I think the last thing I did was just to say, okay, if this was for a massive particle. Of course, if we were talking about a massless particle, such as a photon, then of course it will be exactly the same, but I cannot use tau as a parameter specifying the path because d tau is always 0. So if it was rather than tau, I'd have to use some other parameter characterizing the trajectory or the path of the photon. So it would be, call it sigma. So for massless particle, right? Rather than tau, I have a sigma, so it would be du alpha over d sigma is d squared psi alpha over d sigma squared 0, and then 0 is minus g mu dx mu over d sigma and dx nu over d sigma, and then the motion is seen, the acceleration is seen, and there will be an acceleration seen for photons as well in some sense. And this would x lambda over d sigma squared plus gamma lambda mu dx mu over d sigma dx nu over d sigma. So it's just the same, just repeating for massless. Now this equation is so important, it has a name. It's called the geodesic equation. And again, it describes the motion of a free particle in arbitrary non-inertial coordinate system. Again, it's a geodesic. Right. This is how much we did last week. It was a somewhat longer reminder just to make sure that you're all with me, because now we're going to run from here on. Any questions before we proceed? This is your time now. There is something which is not clear in the algebra, in the physics. Any questions? What, no questions? Everything is clear? We're still clear. You could all answer all the problems at homework without any problem. Okay, so everything is clear and everything is clear. Okay, remember what it's not terrible. There'll be worse things, trust me. No, it's okay. It's not too bad for now. Okay, now what we did so far was purely math, right? I didn't really do much of the physics. The physics came in the equivalence principle and the idea of computational redshift. Everything else we did here in this calculation was just the math. Right. However, of course, what we want to do is to give some physical interpretation. Now, we already have some sort of physical interpretation because, you know, if you're looking at the geodesic equation, right, this is an acceleration term, and the acceleration is associated with the affine connection. So in some sense, right, the acceleration, right, why do we see acceleration? because there is gravity, right? We're saying that something is falling down because there is a gravitational field. So in some sense, the affine connection will get the physical interpretation of a gravitational force somehow. Not exactly, it's not going to be so simple, but it's connected to the gravitational force, right? Right. Now, so the affine connection is related to gravitational force. The proper time interval, right, the tau, we wrote it down as a function of g mu nu, the metric tensor. So there should be some obvious connection, right? Since the proper time is a function of the g mu nu, of the metric tensor. There should be some connection between the affine connection and the metric tensor. Now, in fact, we're going to show it right here, right now. The connection is the derivation, the derivative. So we can get the affine connection from the derivative of the metric tensor. And when we do that, that means what would be the quantity that we derive that give us a gravitational force? The force is the derivative of what? You know the answer?
Momentum.
Of what?
Force is derivative of the momentum.
No, force is not derivative. It's not derived from the momentum. The force is derived from what?
Energy.
Close. Potential. Right? The force is the derivative of the potential. Yeah. Okay. So in some sense, we'll say that one of the interpretations of the G mu nu of the metric tensor would be the gravitational potential. Okay, let's see how we do it. So, okay, the relation between the affine connection and the metric tensor. So we start from the metric tensor, which is given here. Well, I can just write it back there. So G mu nu is just eta alpha beta d psi alpha over dx mu d psi beta over dx mu. Right. Now we're going to take it, the derivative of that with respect to x lambda, right? So d over dx lambda. That's going to give us d g mu nu over dx lambda, which d squared psi alpha over dx mu dx lambda d psi beta over dx mu eta alpha beta. Eta I don't need to just put it on the side, right? Because it's just fixed, right? Remember that the -1 plus, so you cannot take any derivative of that. Plus the second term dx psi alpha over dx mu d squared psi beta over dx lambda dx mu eta alpha beta. Okay. Now we have the definition of the affine connection, which is defined here, right? So we have the second derivative, and then there is dx lambda dx psi alpha. So I can write down, I can just switch the order of that and write down that d squared psi alpha over dx mu is just gamma lambda mu nu d psi alpha over dx lambda. Right, that's from the definition of the affine connection. So, right, if I use this definition, right, so I have it here, plug it in here. So I end up with d g mu over dx lambda is gamma. Yes, I have is mu and lambda, so I cannot use lambda. Let's say something else. It would be rho mu lambda, right? Because I have the mu and lambda here. There has to be a mu and lambda at the bottom, and then the top I'll just pick up a different index. So they're all dummy indexes anyway, right? Times d psi alpha over dx rho times what is left, d psi beta over dx nu eta alpha beta. All right, so this is for the first term. Now I have the second term. So again, for the second term, I have these lower indices would be lambda and nu. Right, lambda and nu. So I have plus gamma to be lambda and nu. And again, I can choose a dummy index at the upper index. So I choose it as a row. Pay attention, I can do that because of the definition of the affine connection. Although the affine connection by itself is not a tensor. So I cannot, the regular rules of transformation do not apply to it. We'll get back to that. Times we have here again d psi and alpha and here. D psi alpha dx here, just copy from here. But then I also have d psi beta over dx. So right, and then beta alpha beta. Okay. But again, what is written here? Gamma rho mu lambda. And what is written here? D psi alpha dx rho, d psi beta dx nu at alpha beta. What is that? Oh, you know, what is that?
Transformation between the coordinates.
No. What is that? What is that? How can you write it in a simpler?
Zero new.
Thank you. Very well. This is just G. Right? This is just G with what indices? What are the indices of G?
Rho and nu.
Euro.
New row, thank you. Excellent. G rho new. And again, for the second term, this one. So we have plus gamma rho lambda and nu G. What are the indices?
Mu and rho.
Yes, thank you. Now, because of the definition, just note that I'm doing something in case you ask yourself, right? Because of the definition of G, right, and of eta, then G is symmetric with respect to mu and nu. I can switch the order. It's okay, it's symmetric. The same goes for the affine connection, right? Again, the affine connection is symmetric with respect to change of mu and nu, right? I can switch the order of indices, no problem. Yeah. So when you're repeating what I'm doing, you say that it's okay to do that. I'm not doing anything illegal. Okay, so that looks quite good, but still not enough. Now we want to get Now comes another kind of an ugly algebraic thing. So now I take that and then I add to that equation the similar equation with exchanging mu and lambda and subtracting the same equation with exchanging mu and lambda. So dg mu over dx lambda plus dg lambda mu over dx nu. No, the opposite. I was getting confused here. Dx mu dx nu minus dg mu lambda over dx nu. Okay, so now you simply have to be quite careful on how you work down all the indices. So again, lambda, rho is just a dummy index. So let's see if I can change the kappa. Mu lambda or lambda mu, and then g and kappa nu plus gamma kappa lambda mu g kappa mu. Right? This is just copied from here. And then now I have to exchange the indices. So instead, this is the same with mu lambda exchange, and this is the same with mu and lambda exchange. So I have here a plus gamma kappa lambda nu. I don't mind that g kappa lambda lambda mu kappa nu plus gamma kappa mu g kappa lambda, right? Just exchange the mu and nu, right? And then minus gamma. Now exchange mu, again, mu and lambda. Exchange. So minus gamma kappa. Now I change mu and lambda. So it will be a mu g kappa lambda minus gamma kappa lambda mu g kappa mu. Yeah. The only thing that you can get confused here is by all these indices. But the math is straightforward, you just have to do it slowly. So this guy and this guy cancel out. And this guy and this guy cancel out. And these two terms are the same. So we are left with 2 times gamma kappa lambda mu g kappa mu. Right. Again, I was making use of the fact that both the gamma, the affine connection, and G are symmetric under the exchange of the lower two indexes. Right? The upper index is just a dummy index anyway. So, of course, the next thing is to define the inverse of the matrix G. So, the inverse metric, right? G mu nu. Of course, we'll have two upper indices. Right? It's defined such that G mu sigma G mu kappa is equal to what?
Delta.
Of course, this is a delta, right? Delta kappa sigma. And then what is left is just to take this equation and multiply it by 1/2 G mu sigma. And okay, so the 2 and 2 goes down. And we have a lambda mu, we have the G kappa mu, G mu sigma. So this is a delta mu kappa sigma. So instead of kappa, I need to put a delta. That means that gamma sigma lambda mu is equal to 1/2 g mu sigma times p g mu over dx lambda plus p g lambda mu over dx mu minus p g mu lambda over dx. Which is what we wanted. So we expressed the affine connection, gamma, in terms of the derivatives of the metric, and we had to use the inverse metric as well. Now this right-hand side also has another name. This is also known as the Christoffel symbol. Christoffel, that's the right symbol. And it also has, the notation is within a curly brackets. So it's also notation, curly brackets, sigma lambda mu. Now, for our purposes here in this course, there is no real difference between the Christoffel symbol and the affine connection. There is a small difference, but again, this is more related to differential geometry than to physics. Never mind, I don't want it's a very subtle thing. It's a very subtle issue, and I might be confused myself in that. So just let you know, in textbooks when you're reading them, which I assume you do on a daily basis, you will see these Christoffels, also called the Christoffel symbol. It has the same practically it's the same as the affine connection, though it's not exactly the same. All right. Yeah. Okay, getting ready. I'm not sure what else is I'm going to get. So now it's going to be quite simple. I'm going to give you an example. So let's look at an example. The metric. The metric is something which can be defined on any space. This is something to realize, right? You don't need to take an especially four-dimensional curved space. It can be on any space, right? And it specifies the space. So the simplified example, the most simple example that I can think of, right, of a non-trivial space is a two-dimensional, a two-dimensional flat space. Let's start with that. 2D flat space. Right. But I'm going to write it in r theta coordinates, spherical coordinates. So what is the element of a length in a 2D space which is written in r theta coordinates? What is the element of length? ds squared is equal to what?
R squared dr and r d theta. R squared d theta.
This very good. So it's
R squared and R squared d theta.
dr squared plus r squared d theta squared. Right? Excuse me for my bad drawing ability. So once you see that, what will be the metric tensor? What is the metric tensor of this 2D flat space?
One and R squared?
Yes, so it's a tensor, right? So it has dr d theta. dr d theta, so it will be 1. What is the term here?
0.
0. What is the term here?
Again, 0.
Again, 0. Now somebody else. And what is the term, the last term? What if you got it properly? What is the term here?
R squared.
R squared. Very good. Right. I just wrote down the element of length in the flat space time. Flat space, there's no time, right? Okay. What's the inverse of the metric? Somebody? Will be here? Guys, all you need to do is to invert
Can I
this.
answer?
Sorry?
No, it's 1 and 1 over R squared.
Right. You're just inverting this matrix. That's all. Right. It looks more difficult than it is because it's very abstract. I'm giving you all the math. Now you just pinpoint it down to earth. Right. Now you can calculate the affine connection. How many terms the affine connections are going to have? By the way, how many terms will it have?
8.
8, right? Because alpha, beta, and gamma can have, you know, R or theta, right? Obviously, most of them are going to be zeros, right? Because there is no dependence on theta here. So every time there is a d over d, you know, theta, automatically it's a 0. So most of them are going to be 0. Only 3 of them are non-zero. So check it at home. Gamma, R, theta, theta are going to be minus R. Gamma, theta, R, theta is gamma, theta, theta, R. Of course, it's symmetric. It's 1 over R. Everything else is 0. Yeah? Okay, do yourself a big favor. Really big favor. And do it at home. You know, dirt your hands. Right? Do it until you realize that this is really the answer. Okay? Don't ask Mathematica to do it for you. Mathematica will do it for you if you ask it in a nice enough way. But do it for yourself just to say that you understand what's going on here. Okay. Now, questions?
Yes, can we have Christoffel symbols in Mathematica?
Yes.
I do have a question. Is there an easy way to guess the affine connections, or we actually need to apply the formula all the time?
I personally don't know of any easy way. No, I don't know of any easy way.
Okay, so it's formula all the time. That's what I'm doing. But okay.
The easy way is to the thing that at least I can see, right? Once I'm seeing a line element of this kind, then they can tell me immediately how the metric would look like, right? Because that's what the metric does, just tell you what is the line element. As for the affine connection, no, I don't know of any. Maybe there is, but I don't have it. You know, just have to work the hard way, or as I said today, what people do when they actually need it for various strange metrics, right? For example, right, you know that there are gravitational waves today, right? So people have to calculate the metric before the neutron stars merge or black holes merge. That's computer knows how to do it, right? Quite easily because you simply give them the formula. I don't know how to do it off the tip of my head without dirtying my hands. Okay. More questions? No. Okay. So the geodesic equation, right? What did we do here? This is the equation of a freely falling particle, right? So particle that has no forces. It's not just that it falls down straight ahead from the sky, right? It might have some initial velocity and there is nothing that prevents it. So it might do some, whatever, parabolic shape. Right. So another thing which is kind of delicate is to know that when I say freely falling or free particle, in Newtonian mechanics, when we say free, that means that it is not being affected by any force, including gravitational force. And in general relativity, it can be affected by gravitational force and still be free, right? Because gravitational force is treated as some curvature of the space-time. So particles are still free, right? Free meaning there are no other forces such as electromagnetic forces that act on them. So, generally in classical mechanics, right? When we speak of a motion of a free particle, that means that it will take the shortest path between 2 points, right? So in the sense that it's reducing the time it takes the particle to move from one point to the other. And in fact, the same thing works here. So this geodesic equation does not only represent the equation of a free falling particle, but this will be the equation of the shortest path in terms of minimizing the time it takes to reach from one point to the other. Right. So let me show you that, and I'm going to show you that using the variational principle, namely Euler-Lagrange equation, which I believe that you're familiar with from your second year classical mechanics. Is there anybody here who's not familiar with the Euler-Lagrange equation of motion? I see that there are a few, but you're ashamed to say, or no, that everybody is familiar with. No, yes, maybe? Okay. Again, refresh your memory. It's not crucial, it's just to show you the point. And the point is that the motion, the geodesic equation really gives you the shortest path between 2 points, namely the path that minimizes the time it takes. So the geodesic equation and the variational principle. Right. One thing is that we are considering what's called as test particles. So when we say a test particle, what we mean is a particle that is small enough so that it does not affect the gravitational field of the surrounding, right? So we can think of ourselves in the gravitational field of Earth, right? We're too small to affect the gravitational field of Earth. This is not the case, for example, as we said, if we speak of merger of 2 neutron stars, of course, and we cannot do this calculation the way I'm doing it here, but it's good enough for us. To speak of small satellite that moves in the gravitational field of Earth or of the sun or whatever, that's a quite good approximation. Right. So, free test particle motion of a free test particle, the shortest path. The shortest path, meaning the path that extremize minimize, be more precise, minimize the proper time between points A and B. This particle is that it's small enough such that it does not affect the gravitational potential. So, not affect meaning can be neglected. So, its effect on the gravitational potential can be neglected. Right, now we said the shortest path is the path that minimizes, minimize the proper time between points A and B. Right, so this is the equivalent of what in Euclidean space we call the straight line. Right, so the equivalent to straight line in Euclidean space. Right, you know how we call these straight lines? And if you learn geophysics, it has a name. How do you call these straight lines? The equivalent of, or the generalization of straight lines to non-flat spaces? Anybody want to guess? No? So hard. Wow. What?
Tangent?
No. I thought you would be familiar with it. It's called geodesics. Are you familiar with the concept? Have you ever? I mean, I guess you're not because nobody said it. You are. You heard the name geodesic? So geodesic is a straight line. I'll give you a demonstration shortly. All right, it's called a geodesic. And the equation of motion is called the geodesic equation. These are called the equation is called the geodesic equation. Okay, so let's actually do it, right? So let's start from the simplest one, from the equation of motion in special relativity. Right? So one, equation of motion in special relativity from the variational principle. So essentially what we do, we want to find the path that minimizes the proper time between points A and B, right, or extremize it. So we said the proper time tau. Let me know what you already done because it's important enough. We want to find the path that extremize the proper time between A and B. Right? There's 2 points in space. Right? The particle moves from A to B. So tau from A to B is just integral from A to B of d tau. Right? So just integral from A to B. Let me choose what is d tau? right? Just eta, alpha, beta. Well, I use tau, so okay, so it has to be some other parameter along the path. So let's call it lambda. D lambda, and then it will be minus 1 over c squared eta alpha beta d psi alpha over the lambda d psi beta over the lambda, the power 1. Right? So lambda is the parameter along the world line of the particle. Right? So we want to extremize tau. Lambda parameter you all with me? Because nobody's saying anything. So I mean, at this point, not saying anything does not necessarily mean that everything is clear to you. I know what I'm talking about. Okay. So, what are we going to do? Use the variational principle, right? So variational principle meaning that we find a path for which when we make a small change, right, of delta psi, then the tau is not changed. But that's exactly the same problem. So let's say we find the path, the shortest path, the path for which tau maybe does not change. And for small change, delta psi. Right. So this, of course, is identical to the problem of you did in Newtonian mechanics, right? So we just like the integrand is just a Lagrangian, and the psi is the dynamical variable, and the lambda would play the role of time here. So the Lagrange equation of motion right, minus d over the lambda, the L over d psi alpha over the lambda, plus the L over d psi alpha, what sigma is here. Not to confuse with the alphas here is equal to 0. And this is really the Lagrangian. So L is just minus 1 over c squared, eta alpha beta d psi alpha over the lambda, d psi beta over the lambda, for 1/2. So what is the L over the psi? What is the L over the psi?
0.
Of course, it's 0, right? L is not a function of psi, just of the derivative of psi, right? So the L over the psi is 0. So the equation of motion, if this is L, so we just left with d over the lambda. Right, we have d over the lambda of the L over d psi sigma over the lambda. So L is depending on that to the power 1/2. So we have 1 over 2L, and then we have minus 1 over c squared. But then sigma takes both alpha and beta, so we just need 2 eta sigma beta d psi beta over the lambda. Well, that really matters because it's supposed to equal to 0, right? Because we have a symmetry. The 2 here is because of symmetry, right? Between alpha and beta. And of course, we made use of the delta function here. And since the L is just the tau over the lambda, then so L is the tau over the lambda, right? Then we can write it down as d over the lambda. And this is just 2 and 2 cancels out. 1 over 6 squared, I don't care anyway because it's equal to 0. And L is the tau over the lambda, so I'm left with the, I should have a sigma here. Doesn't really matter. B sine sigma over the tau is equal to 0. So just multiplying. Right over here, did I miss anything? I think it's my mistake. So anyway, okay. So now we just multiply by the tau over the lambda over the tau, and that gives us d squared sine sigma over the tau squared is equal to 0, which is of course the equation of motion for a free particle. Okay, since it's not clear to me that you all follow me. It's not a particularly difficult exercise that I just did here. I just derived the equation of motion from the variational principle, which you all say you're all supposed to be seeing in your second year, right? I just wrote down tau, right, is the proper time between point A and B, just integral over the tau, right? The tau, right, is just the lambda times, I express it with an eta, right? Eta alpha beta, d psi alpha d lambda, d psi beta d lambda, right? To the power 1/2 of that. And then I said, okay, now this is analog to the Lagrangian. So this will be the Lagrangian L, right? Lambda is simply a parameter. Right? The Lagrangian here would just be the tau over the lambda. And then I can just use the Lagrange equation of motion, the same format you're familiar with, and just plug it in, plug in the expression for L. And I immediately, automatically, nearly, right, get down the equation of motion, which is the same equation of motion for a free particle. What I just did here was to show you that in the freely falling coordinate system, the equation of the, the path that the free particle takes is indeed the path that minimizes the time between points A and B. Nothing is surprising here, physically. Right? Questions, guys? No, I am concerned by the lack of questions at this point.
Asaf, what I don't get is you said that L is the integral over the tau, and then you said that it's the tau over the lambda.
Well, I just expressed the tau. I mean, from here, where is it? From here, right? It follows immediately, right? Just L, I can express it as the tau over the lambda. It's written, I have integral from A to B of the tau, which is equal to the integral of the lambda times the tau over the lambda.
Okay, now I see.
Right? That's all. I just wanted to avoid using the same symbol. Yeah? More questions? No? Let's do the same now for GR. If this is clear, then you should be able to do it right away, right? So let's do the equation of motion. For free particle. in GR from the variation principle. So, of course, it's completely analog, right? It's exactly what we did. So we take the extremum. Tau A to B, integral from A to B of the tau. So it's integral the lambda of minus 1 over c squared, g alpha beta dx alpha over the lambda, dx beta over the lambda, the power 1/2. So of course now the Lagrangian, L minus 1 over c squared, d alpha beta dx alpha over the lambda, dx beta over the lambda, to the power 1/2. And the Lagrange equation. Right. D over the lambda of dl over the lambda over d xi lambda, right? So this will be again what we had previously, 1 over 2l minus 1 over c squared to g sigma beta dx beta over the lambda. But now on the right hand side, we need to take the derivative of L with respect to x, right? Not just the x over the lambda, so with respect to x. And that can occur via g. So we have minus 1 over c squared, 1 over 2l, and then the g alpha beta over dx sigma dx alpha over the lambda dx beta over the lambda. Right, so now we have this extra term, comes from the fact that g may be a direct function of x's. So again,
I think it's plus 1 over c squared.
why should it be plus? I moved it to the other side. So I ended up an extra factor of minus. Here it was a plus right here, and then but now I took it and I move it to the other side. So again, an extra factor of minus here.
Yeah, but you have already a minus, so it's minus minus. You have the minus 1 over c squared.
What did I miss here? What did I miss here? No, but then I ended up an extra minus on the left-hand side as well. Because I have in the left-hand side, I also have this minus. Because in the left-hand side, I also had this minus here, right, which I neglected. So I ended up with this extra minus, which is missing here. So I'm good at the end. But you're right that this was a bit confusing. Right, so I can either have a plus here, I can either have a plus here and a minus here, or just switch the order. Okay. Good spot. And so this ends up with the same the same as what we had previously. So this left-hand side is just the over the tau g sigma beta dx beta over the tau. And on the right-hand side, I have to put now L again. no, sorry, okay. So I multiply by, wait, let's, okay. What did I do? What did I do here? What I wrote is 1/2, and then okay, no, I did something which is simpler. So the minus 1 over c squared, the 2 and the minus c squared, so the 2 is left, the c squared and the c squared cancel out, that's okay. The 1 over L is the tau, the lambda over the tau. So I can simply use that here to get a dg alpha beta over dx sigma dx alpha over the tau. That is one of the taus, and then dx beta over the tau. I get that by multiplying again by the lambda over the tau. As I did previously, I ended up in the left-hand side. So that's okay. And so the equation of motion that we have here, which is this, I can write it down as dg, okay, let's start from here, dg sigma beta over dx mu over the tau, dx beta over the tau, plus g sigma beta d squared x beta over d tau squared, minus, now I take the right hand side and move it to the left, so minus 1/2 dg alpha beta over dx sigma dx alpha over the tau dx beta over the tau is equal to 0. Is equal to 0. Okay, that looks annoying, but now you must note the symmetry between alpha and beta. There is symmetry here, and then I can reshuffle the dummy indices in the first term, right? Mu is a dummy index. So I can write down, let's see, g sigma beta d squared x beta over d tau squared plus 1/2. Okay. Since this is a dummy index, I can change it. So I can do it dg sigma beta over dx alpha, dx beta over d tau, dx beta over d tau, plus dg. Now, instead of this dummy index mu, I can write it down as sigma again, alpha, sorry, dummy index here would be a beta, dx beta. So dg alpha sigma over dx beta minus dg alpha beta over dx sigma times dx alpha d tau, dx beta d tau. This is equal to 0. Okay, I made a small game here, writing down this term as 1/2 of the sum of the terms when I shuffle the dummy indices. And then, of course, what is left is to multiply by the inverse metric g sigma rho, which gives us the equation of motion for a free particle, which is simply the geodesic equation, which again gives us multiplied by the inverse. Then I ended up here with a d squared, that's rho over d tau squared, plus, of course, this is the gamma rho alpha beta dx alpha over the tau dx beta over the tau is equal to 0. Which, of course, not surprising at all, is the same equation that we derived previously. But now what we did is to write down, this is the equation of motion for free particle. Or the geodesic equation in curved space-time. Right. Of course, alternatively, we could write down the same equation, not using the coordinates, but using the velocity, right? du rho over the tau plus gamma rho alpha beta u alpha u beta equal to 0, right? Which is, of course, the same equation. Now, again, for photons, right, they will be traveling along null geodesics, right? So, null word line. So for photons, right, they travel along what is called a null word line. Tau is equal to 0. So the path has to be characterized by a different parameter, not tau, but something else. It can be lambda or sigma. So we can write down x alpha is x alpha of lambda. And the equation of motion is, again, the same equation of motion for null geodesics. Right. D squared x rho over d lambda squared minus gamma rho alpha beta alpha over d lambda dx beta over d lambda, where lambda here is a parameter along the path of the photon. Right? These are null curves, and null curves that satisfy this equation are known as null geodesics. And of course, light waves move on null geodesics in the path of the light. Okay, questions? Too short. I didn't really do anything really here. I just used twice the Euler-Lagrange equation of motion. That's it. Now, okay, just to give you a feeling that you actually know exactly what I'm talking about, even if you don't understand anything I say, which I don't believe is the case. I believe you understand something. How many of you ever flown to the US? You can raise your hand, right? Now, I'm sure you've seen on these screens, right? You're seeing in these screens, right? There are these small screens that show you the trajectory, right? So, we are here. This is Europe, Mediterranean. This is Israel. This is England. Right? This will be the US. Right? US, Canada. Here will be Greenland somewhere. Right? And we are flying from Tel Aviv. Right? How does the trajectory goes? Let's say that this is New York. This is Tel Aviv. How is the trajectory going? Is it going straight?
It's in a
No.
circle north and south. It goes in a big
Right,
circle.
right. Why is it going? It's always going like that, right? It takes you close to Greenland. Why is that? What is the trajectory that the airplane is flying?
Geodesic?
Of course. Does he have any interest in taking you to see Greenland? What is the interest of the company?
Save fuel.
Save fuel. They want to take you the shortest path, right? What path are they taking? Of course, the subject, they have a limitation. The airplane cannot go through the Earth. Has to go around the surface of the Earth, right? And so just for a demonstration, I happen to have here, say this is a globe, right? My favorite demonstration tool in this course. I don't know if you can see it. This is Tel Aviv here, right? This is the US. Now, of course, in the spirit of what we have here, right, I have a mask. So I'm using this as a rubber. And if you want to know what is the shortest path, which is subject to the constraint that you're moving in a spherical surface, right? I can simply put one end of that in Tel Aviv, let's say here. Then I just squeeze it. And let's say I put the other end in Los Angeles. As you can see, I hope, the shortest path between Tel Aviv and Los Angeles actually takes you through Greenland. And the shortest path between Tel Aviv and New York, right, I'm saying, I'm not cheating, actually will take you slightly south of Greenland, but not much. Right, of course, this map is lying, right? The map here is lying. Because what this map here is doing is trying to take a 2D sphere, which is not a Euclidean space, right? And map it onto a 2D flat space. This is not a flat space, right? So yeah, and the path that the airplane takes is described by which equation?
Geodesic.
Geodesic. All right, so you can actually now, you just need to write down the metric of a sphere, 2D sphere. You can calculate the affine connection, and you know exactly what will be, how to calculate the trajectory. You'll have to do it in one of the closed problem sets. I may even post it today in the next problem set. All right. Now you can try it. It's actually quite a fun game. If you want to fly, let's say from New York to Beijing, for example, then the path will take you nearly around the North Pole. I did it once myself. Kind of interesting. Actually, it's quite boring. The North Pole, there's nothing to see. But yeah, play with that a little bit. Have your own globe, or I don't know whatever you're going to do it. But just play. That is exactly the equation that describes that. Just prove it right now. That's what it really means. Questions?
Can you upload the notes to the Moodle?
Yeah, I'll do it today. Today or tomorrow. Yeah, I'll do it. We're nearly finished with this section, and then we'll go to the next section. Guys, it's good that you want my notes. You'll have them. I did not invent them, right? I just read them in books. And well, I did that of some by myself. I definitely added, but the idea is that you also go to the library or to the virtual library, and it's all there in the books. Okay, I did not invent these things. I just took them and I delivered them to you. Yeah, I'll put my notes. Any further questions? Problems? Guy, believe me, it's not very hard. It's very confusing. Don't get, there is a difference between hard and confusing. It's not so hard, but there is a lot of subtleties in the math. You nearly got me confused, and these are things that I've been going through many, many times. So go through it, do it carefully. You know, on these things that are confusing, you simply have to do it carefully. It's not very difficult. If you find it difficult, then ask me. But I don't think you'll find it difficult once you do it slowly enough. Okay, but do it, because it will just get worse. So believe me. So do it now to make sure that there are no subtleties and no missing links or anything, so that we can really focus on the hard things, on the physical stuff around it. Okay, do the math, do it carefully, and do it. Don't wait for my questions, and obviously don't copy the answers from somebody else who might know them. Do it yourself, go yourself and practice it. If you want, I can hand you more problem sets. I don't want to give you more problem sets just to give you problem sets, because then somebody has to grade them. But I do want you to practice, and you realize this kind of things we need to practice. If you are to, once you practice, then it's not as terrible as it sounds, as it looks in the first time. All right. Any further questions or comments? No. If not, then I'll see you on Thursday. And right now, I don't expect any further missing lectures. There will be in 4 weeks' time. There is Shavuot, but until then, we have people to move on. So I'll likely post the next problem set today. I'll check out. Yeah, likely. I'll see. If not, then maybe check out the website. All right. Good seeing you all, and see you again on Thursday, I believe.
Thank you.
Thank you.
Sap, can you stay a minute so we can talk?
With the recording, yes, I can stay a minute.